Hello, my name is Stephen Roman. I'm a retired professor of mathematics. My website is www.sroman.com. This is the second in what I hope will be a series of lectures on elementary category theory. I want to first thank those people who responded, left comments on the first part of the series. I appreciate that. It helps me decide whether to continue the series or not. In the first lecture, I tried to motivate the notion of a category. We talked about abstraction and how that can be a unifying and clarifying concept in mathematics. As an example, we talked about uniqueness of inverses in various contexts and how that became clearer in the abstract context of a group. I defined categories for you. A category consists of a class of objects, and for each pair of objects A and B in the category, there is a Hom set, which is a set whose elements are called morphisms, maps, or arrows. A composition exists between morphisms that are compatible for composition, and that composition has to be associative. And also there is an identity arrow for each object. We also talked about what I refer to as the two tenets of category theory, the first of which is that morphisms are on an equal footing, are just as important as the objects that they morph. And that's why in the definition of category, the morphisms play more or less an equal role. Also, many different types of mathematical constructions are best described using morphisms rather than using elements, or at least a description in terms of morphisms brings out certain important properties that are not so obvious when the concept is defined in terms of elements. And the example I gave was the direct product of vector spaces and the role of the projection maps. So we defined a direct product as a triple where this is V cross W is the Cartesian product, and row 1 and row 2 are the respective projection maps. And we talked about the universal property that that triple has, and that is in fact the main characterizing property for direct products. So today I want to start with a little discussion of functors. If we are going to follow the tenets of category theory that I outlined before, then since categories can be thought of as objects, we need to discuss morphisms between categories, and those are called functors. So if we have two categories, C and D, how are we going to define a morphism from C to D? Well, categories have two parts, really. They have objects and they have morphisms. So what we're going to need is two functions. One that maps the objects of C to the objects of D, and one that maps morphisms in C to morphisms in D. It's customary to use the same letter, F, for both of these functions, and I'm going to use a double arrow to denote functor. So a functor from C to D is going to have two parts. First, it's going to have an object part, which is a map, again denoted by F, that sends the objects of C to the objects of D. And this I call the object part of the functor. It's going to have an arrow part, which is a function from the morphisms of C to the morphisms of D. But we have to be more specific. There are actually two kinds of functors: covariant functors map the local morphisms, say the morphisms from A to B in C, to the morphisms in D from FA to FB. Okay, so that defines the arrow part of the functor, and the restriction of F to a Hom set I usually think of as the local arrow part, or a local arrow part of the functor. In the contravariant case, F maps the Hom set Hom AB to the Hom set Hom FB FA. So the difference here is that there's a reversal of direction. These are morphisms from FB to FA. We need some properties. Let's see if I can get this in the camera here. Not very well. Okay. Morphisms have to preserve the structure of a category, so they're going to have to map the identity at A to the identity at FA. This is the morphism or arrow part of the functor. And we'll have to preserve composition. So in the covariant case, F of G circle F has to be F of G circle F of F, and in the contravariant case, F of G circle F will be F of F circle F of G. So, again, a functor from one category C to another category D is actually two functions. The object part is a function that takes objects of C to objects of D, and the arrow part takes morphisms in C to morphisms in D. A covariant functor maps Hom AB to Hom FA FB. So in other words, it takes a morphism from A to B to a morphism from FA to FB. A contravariant functor takes a morphism from A to B and produces a morphism from FB to FA. The direction is reversed. Both types of functors must take the identity map at A to the identity at FA, and in the covariant case, composition is preserved. In the contravariant case, composition is reversed, otherwise preserved. And again, F restricted to one of these Hom sets I refer to as the local arrow part of the functor. So you can think of a functor as a map from objects to objects, and then a bunch of maps that take Hom sets to Hom sets. One way to view a functor that I think is helpful is that it's a map from one arrow diagrams like this to, in the covariant case, one arrow diagrams like that. In the contravariant case, it would be just, you would switch FA and FB. And the two conditions, this first one here about identities, says that a loop is taken to a loop, and that the second condition in the covariant case says that a composition so a triangle like this is taken by a covariant functor to the same triangle with F applied to everything. So this is going to be F of G circle F, but that is equal to FG circle FF. So this is in the covariant case. I'll leave it to you to draw the pictures in the contravariant case. I just have to reverse arrows over on this side. Okay, so it's not a bad way to think of functors as mapping one arrow diagrams to one arrow diagrams, mapping loops to loops, identity loop to identity loop in particular, and preserving triangles. Functors can be composed in sort of the obvious way. You just compose the, let's say we have F mapping C to D, and G, is capital G, mapping the category D to the category E. Then G circle F, the object part will take an object of C and give you an object in E. And the morphism part will take a morphism and give you this morphism. Okay, so composition is pretty straightforward. It's just composition of object parts and composition of arrow parts. There are some special types of functors. First, a functor, let's say F is a functor from C to D. F is called full if the local arrow parts, that's all of them, are surjective. So that means that the local arrow part, Hom AB to Hom FA, FB, at least for the covariant case, that this is surjective. Okay, so then the functor is said to be full. f is faithful if the local arrow parts are injective. So two distinct morphisms between A and B, from A to B, will be sent to distinct morphisms from FA to FB. And we can combine these two, and we have the term fully faithful. That means both full and faithful. So in that case, the local arrow parts are bijective. There's another term related to this, and that is embedding. And as it happens, this is defined differently by different authors. Some authors define an embedding as simply a fully faithful functor. There are other definitions. The one we're going to adopt is the strongest one. And so F is an embedding if F is fully faithful and the object part of F is injective. If that doesn't happen, all sorts of things can happen. If different objects in C are mapped to the same object in D, then different morphisms, or morphisms from different Hom sets, will be mapped to the same Hom set, which is in general probably not what you would prefer. So when the object part of a functor is injective, then the Hom sets remain separate. So if you have A and B here, and you got all these arrows for the Hom set, they get sent by to FA, FB, and you'll have all these arrows here. If you have, let's say, C and D over here, they will not be mapped. C will go to someplace different than A, and D will go to someplace different than B, and so these arrows will be different from these arrows, and it's a much cleaner situation. Okay. Well, let's look at a couple of examples of functors. Power set functor. I'll call it P. So this maps a category C to the category of sets. And P of A is the power set of A. And if we have a morphism from A to B, so that's just a plain old set function, PF maps PA to PB, and it is the induced function. So what is the induced function? PF just takes a subset S, so S is a subset of A, then this is the set of all F of S's, S in S. So as you probably know, if you have a function between two sets A and B, then subsets S are mapped to subsets in B. You just map all the elements. This is called the induced function. It's usually just denoted by the same symbol that the original function is denoted by. Okay, and you can check that this is indeed a functor. It's covariant. There is a contravariant version of the power set functor. I'll just call it F. Again, it takes a set A to the power set. So that's sometimes denoted by 2 to the A. If F maps A to B is a set function, then FF maps 2 to the B, the power set of B, to the power set of A. And what's an obvious map that does that? The induced inverse map. So this is F inverse. So again, with our picture, A, F, B, sets over here, S gets sent back here to F inverse of S by just finding everything in A that's mapped to S, and that's F inverse of S. So there's no requirement of injectivity or bijectivity or anything like that. Okay. So this guy is contravariant, and the composition rule is this. Here's another really important example of a functor. Oftentimes, if we have a category C, the objects are sets usually with additional structure. And the morphisms are set functions that preserve the structure. So group is an example. The objects are groups, but they're also sets, and the group homomorphisms are set functions that preserve the group structure. The algebraic categories, ring, vector space, and so on, they all fit this model. The objects are sets with additional structure, and the morphisms are functions, set functions that preserve the structure, topological spaces, manifolds, and so on. So this gives us an opportunity to define a functor. F from C to set. And what does F do? It forgets the structure. So in the case of group, for example, F maps a group G to G itself, but on the left we think of G as a group, and on the right we think of it just as a set. So this belongs to set. We forget the group structure. And a group homomorphism, from G to H, is sent over to the same function, but just thought of as a set function rather than a group homomorphism. So we forget the fact that F preserves the group structure. You don't have to always forget everything. We could take a functor from commutative ring, or ring, to abelian group, where we take a ring R and we forget multiplication, but we retain addition, and so we think of a ring as an abelian group, an additive abelian group, and we think of a ring morphism as a group homomorphism of the abelian groups. So that's forgetful functor, but it doesn't forget everything. Okay. We'll see some additional examples of functors as we proceed through the lectures. What about the category of all categories? Now that we have functors, which are morphisms between categories, can we not think of the categories as objects of a big category and the functors as morphisms? Well, yes and no. We get into a little problem here with the foundations because of the word all categories. If this was a category, call it C, then it would have to belong. Well, there's two issues here that are possible. First of all, the category of all categories, if it's going to be anything, the collection of all categories has got to be a class. It's too big to be a set. So if this is a class, then C itself, being a category, will belong to itself, which is not permitted for classes. If, for some strange reason, the collection of all categories is actually a set, we have a different problem. C would still belong to itself, and one of the axioms of set theory, the axiom of regularity, implies that no set can be an element of itself. So regardless of how this turns out, if you don't want to believe that the collection of all categories is a proper class, and you want to believe it's a set, which really isn't correct, but if you wanted to believe that, you'd still run into a problem. So there's no way out of this. The collection of all categories with functors as morphisms is not a category. But category of all small categories is okay. Remember that a small category is a category whose class of objects is actually a set and whose class of morphisms is a set. So we've got a set worth of objects and a set worth of morphisms. Now we don't have the same problem. This is a category, which I'll call C again, and because C is a large category, it does not belong to itself because it's not small. So that's the way out. Okay. Despite the fact that we have the two main tenets of category theory, we can't dispute the fact that most categories have the property that, most categories that we're interested in studying have the property that their objects are sets, and that the elements of those sets are important. And also the morphisms are functions between these sets. They're set functions with some additional structure. So that leads us to make a definition, and that is a category is concrete if in spirit, I'll say it again, this is informal now, this isn't the formal definition, the objects are sets, or can be thought of as sets anyway, somehow, and the morphisms are set functions. So the official definition is if there is a faithful functor f from C to set. So a faithful functor, first of all, the objects then are getting mapped to sets. The possible problem here is that different objects can get mapped to the same set. But if you think about the category group, for instance, different groups will be the same set. Right? I mean, you can define group structure on a set in different ways, and so you'll get different groups, but you'll have the same underlying set. But also, the functor has to be faithful, which means the individual Hom sets. This is usually functors are covariant unless it's specified otherwise explicitly, that this is injective. It doesn't have to be bijective, because we're only interested here in thinking of morphisms in the category as being, now this one over here is in the category set, this is C. So we're talking here about set functions. So we're only interested in thinking of morphisms as set functions, and different morphisms as being different set functions. This is different from the notion of a forgetful functor, where the local arrow parts don't need to be injective. So if we're forgetting structure, then two distinct group morphisms, for example, may be the same function. But here we are talking about a different concept. What we are saying informally is that every object can be associated with or thought of as a set, and every morphism from A to B can be thought of as a set function, but different morphisms are thought of as different set functions. Categories that are not concrete are called abstract categories. And the truth is, it's not always easy to tell whether a category is concrete or abstract. The question does get a little complicated, and it's probably out of place for this introduction. The category REL of relations that we talked about before, its objects are sets and its morphisms are relations. This is abstract. Other categories that are abstract are a little bit harder to find. There is a very important result in category theory called Yoned's lemma, in the Yoneda embedding, which we hopefully will get to in quite a few more lectures. And it actually implies that all small categories are concrete. That is, specifically, there you can find for any small category a faithful functor from C into set. You can also talk about subcategories. The idea informally is that if we take a category C and we throw away some objects, and whenever we do that we have to throw away morphisms that either enter or leave those objects, we will get a smaller category. We might further want to throw away some morphisms in some Hom sets without throwing away the domain or codomain. but that has to be done a little bit carefully too, because we have to preserve the composition. But when we're done throwing stuff away in an appropriate fashion, if what's left is a category, then that's a subcategory. More formally, D is a subcategory of C if the objects of D form a subclass of the objects of C, and if for every pair AB of objects in D, Hom D of AB is a subset of Hom C of AB. We can say subset because if you recall, our definition of category requires that the Hom sets be sets, so that the category is already locally small. Also, the identity map in D for an object, again, A is in D, the identity map in the subcategory has to be the one that came from C, that already exists because it's in C, because C is a category. And that composition in D is the composition from C. Composition in D is the composition from C. So there's already a composition defined on the morphisms in D because they are morphisms in C, and that composition defines the composition in D. So that makes a subcategory. So some simple examples. A abelian group is a subcategory of group. Every abelian group is a group. We can keep all the group homomorphisms. So this is what is referred to as a full subcategory. Because the subset relation here is actually an equality. So that's what makes a subcategory full. One curious thing happens here that we need to discuss. For example, if F is a group homomorphism, then as you know, F of G, the image of G, is a subgroup of H. If, for example, tau is a vector space, a linear map, then tau V is a subspace of W. But for categories, it doesn't work that way. If F is a functor from C to D, then the image FC need not be a subcategory of D. What happens in the case, for example, of group homomorphisms is that the image FA, image FB, that this product being F of AB will be in F of G. So that's closure under product, and inverses follow and so on. But something can happen with categories because the role of product is played by composition, and not every pair of morphisms is compatible with composition. So for example, if we have, let's say here's our category C, and we have A here, and a morphism from A to B, and another morphism G from C to D, and here's our functor F, and over here FF gets mapped from X to Y. So A is being sent to X, B is being sent to Y, and F is being sent to a morphism between X and Y. And C is sent to Y, so B and C are both being sent to Y. Okay. And D is sent to Z, so G is sent to FG here, going from Y to Z. On this side here, this is all part of the image of C under F. The composition here looks like that. That has to exist if the image is a subcategory. The problem is that's not equal to f of G circle F, because G circle F doesn't even exist, because F and G are not compatible for composition. Now it could happen that this map accidentally is in the image of the functor, but it doesn't have to be when G circle F is not defined. If G circle F is defined, then everything will be just fine. Okay, so just like by analogy up here, A times B, if for some reason that wasn't defined, then you wouldn't be able to write this. You wouldn't know that FA times FB was in fact in the image of the functor. Okay. But that's not the case, because product is always defined. Composition is not always defined. So that's what can happen in categories in general. Okay. If the object part of F is injective, then we have no worries. The problem we had here was that B and C both went over here to Y. And that's what created the issue here. Okay, so I'll let you sort this out and show that if the object part of F is injective, then the image FC is a subcategory of D. Okay, the next topic that I want to discuss are what is referred to as diagrams in categories. Here there's a simple informal definition which unfortunately is lacking, and so there's a formal definition as well. The idea, or the informal way of looking at diagrams, is simply a picture of a portion of a category. So we can do that very simply by drawing some dots and labeling them with objects from the category. So C is a category, and A, B, and C are objects. Okay, and then draw some arcs. So those are directed line segments. Maybe I'll go this way on that one, and label those arcs with morphisms. And obviously we want F here to be a morphism from A to B, and G to be a morphism from B to C. Okay, and that's a diagram. A little bit more formally, what we do is we draw what is referred to as a directed graph or digraph. This is a concept from combinatorics. It just consists of nodes and arcs. There can be loops, but they're all directed. They all have an arrow, a direction. Okay, and then we label the directed graph. We label the nodes with objects and the arcs with morphisms. And we can label two distinct nodes with the same object if we want, and in which case it's possible that two distinct arcs will get the same, will be labeled by the same morphism. One thing we want to avoid, however, is to have two arcs between the same two nodes labeled with the same morphism. We don't want that, and I'll discuss that a bit later. But otherwise, we don't have any restrictions. The problem with this definition, it's quite suitable for many things, but when it comes time to define the category of all diagrams in a category C, it's a little bit lacking. It becomes much more difficult to make a good definition. So there's a more formal definition of diagram, less intuitive and more formal. Let J, script J, and script C be categories. Okay. A diagram in C with index category J is just a functor. J from script J to C. So we better have a picture right away. Over here is our index category, script J. And then here is our functor, sorry about that, functor J. And that goes, let's say, just as an example, here's Jm, and here's Jn, and so this is J alpha, and let's have this be the same as Jp. So this is JQ, and this is J beta. So this is what's happening in, this is actually in the image J of script J, and all that is inside C. Okay, so that's a picture of a formal diagram in a category C. The index category J has only one real purpose, and that is to uniquely identify what you might call the nodes and the arcs in our diagram. Okay. This formal definition is the definition we will want to use when we define the category of all diagrams, but when we are doing things like categorical constructions, like if you remember the direct product of vector spaces with our projection maps and the universal property that we talked about before, that's a diagram. The nodes typically aren't denoted by dots, they're just denoted by the labels. I could put the dots here, but there's no real need for it. Okay, and there'd have to be one here too. Okay. So this is a diagram, and we don't need to think of it as a functor from an index category in cases like this. When the functor is an embedding, then the objects, which is not the case here, then objects map injectively to objects over here, and morphisms will map injectively to morphisms. We don't really need the index category at all. Once we make a picture, then the nodes and the arrows are uniquely identified by their position on the paper, in fact. So we don't need the index category. That's why pictures like this are usually what you see for diagrams rather than pictures like this one up here. A diagram is said to be commutative or commute when all paths between two nodes produce the same morphism. So if we have a diagram, here's a bunch of nodes, and we have these arcs. Let's say this is A, B, C, D, F, G, H. Then the path from A to D, the directed path, we think of as being, I'll draw it here, we think of as being labeled with the composition, H composed with G composed with F, like that. So if we start, for example, here at X and we want to go to V, there are two different paths. One is just this one arrow path labeled F. The other is this path here, which would be labeled row 1 composed first tau, then row 1 this way. And the other path is F. And to say that this diagram commutes is to say that these two paths are labeled with the same morphism. And that has to be true for all pairs of objects and all paths, pairs of paths between them. But there is one exception. It's a technical exception. This is a diagram, and there are two paths from A to B, and I would like to be able to say that a diagram like this commutes, or a bigger diagram, specifically, we're going to be looking at diagrams like this, that there are two paths from E to B. One is first E and then F, and the other is first E and then G. And I'd like to be able to say that this diagram commutes if those are equal. But there's also two paths from A to B. One's F and one's G, and so the way I've defined commutativity of the diagram, F and G would have to be equal. So what I have to do is amend the definition I just gave to say that any two paths from A to B where at least one path has length greater than 1 must give the same morphism. Okay, so that's the proper definition. A diagram is commutative if, given any two objects in the diagram and any two paths between them, one of which at least has length more than 1. In other words, they don't both have length 1, then the two path morphisms have to be the same. So this will be a commutative diagram if and only if this holds. We don't have to require that F and G be the same morphism. I want to talk about another topic which I think is not very fashionable these days in category theory. It's kind of an older topic, But I think it's helpful to give a little perspective to things that are going on here, so I want to do it. I'm just going to refer to this as special types of morphisms. Among set functions in the category set, there are some morphisms that are set functions, some special set functions that you know pretty well. Invertible functions, so we've got right and left invertible, one-sided invertible, and two-sided, and also right and left cancelable functions. So a function, for example, is right cancelable if h composed with f equals g composed with f implies h equals g. See, if f is on the right, you can cancel it. You also have the notion of injective and surjective functions. So we've got three sets of concepts, a left and right pair. Invertibility, cancelability, and injectivity and surjectivity. In the category of set, these are related. Okay. Right invertible, right cancelable, and surjective, these are all equivalent in the category set. And left invertible, left cancelable, and injective are equivalent concepts in this category. But what about in arbitrary categories? Well, the first problem is injectivity and surjectivity are not categorical concepts because they are defined in terms of elements and not morphisms. So when we are discussing arbitrary categories, those two concepts disappear. So that leaves us with invertibility and cancelability. But in arbitrary categories, those two concepts are not equivalent. We should set down for the record some definitions here. So F is a morphism in a category. It's right invertible if there exists a morphism FR. Okay. And this goes from B to A such that F composed with FR is 1B. So that's a right inverse. That would be, FR would be called a right inverse for F. That's a categorical concept. We're dealing only with morphisms here. We're not dealing in composition. We're not dealing with any elements. Left invertible, of course, would be quite similar, and I'll leave that for you. And then just plain invertible, if there exists a G mapping B to A such that F circle G is 1B and G circle F is 1A. And then G will often be written F inverse. Okay. So that's called a two-sided inverse. This is also, F then is called an isomorphism. And A and B are isomorphic objects. The concept of an isomorphism is categorical. Isomorphism is a categorical concept, the way I have defined it. Okay? But this leads to kind of an interesting observation. For example, in categories where the objects are sets and the morphisms are set functions, like in the category set, group, ring, vector space, and so on, there's two definitions of isomorphism. There's the categorical definition, and that's a morphism with a two-sided inverse. And there's the non-categorical definition, which is a bijective morphism. Now, in the case of most algebraic structures, such as rings and groups and vector spaces, these are equivalent. But they're not always equivalent in categories, maybe some that you would think at first that they were equivalent. Suppose we have a partially ordered set, P, with two elements A and B that are not comparable. Sometimes they're called parallel. Now we have another partially ordered set with two elements, 0 and 1, that are comparable. And suppose we map F here. F takes A to 1 and it takes B to 0. So F maps P to Q. F is bijective. F is monotone. In other words, it preserves the order, but it is not an isomorphism. It's not an isomorphism because 1 is bigger than 0, but F inverse of 1 is not bigger than F inverse of 0. So this is a bijective, if you will, homomorphism of posets that is not an isomorphism. It does not have a two-sided inverse. You can prove the usual kinds of stuff. For example, when two-sided inverses exist, they are unique. And if a morphism has both a left and a right inverse, then those two inverses have to be equal and are a two-sided inverse. And the usual formula for the inverse of a composition when it's defined. And all that stuff is pretty routine. I mentioned already what right cancelable means. So that's F is right cancelable. If G circle F equals H circle F implies G equals H. And left cancelable will be very similar. I don't need to write that out. Right cancelable morphisms are called epics or epis. And left cancelable morphisms are called monics or monos. I really dislike these terms. There's nothing wrong with right cancelable and left cancelable. It's perfectly good terms, and this is just one more thing to have to remember, and it's really easy to confuse. Is right cancelable epic or monic or mono? And it's unfortunate, but those are the terms. In general, invertibility is stronger than cancelability. I guess that's probably not surprising if you think about it. A left invertible morphism is left cancelable. A right invertible morphism is right cancelable. So if morphism is invertible, it's both left and right cancelable. Those are fairly obvious things. It's true, however, that a morphism that's both left and right cancelable doesn't have to be invertible. And you can find an example of that in the categories we've already discussed. If you boost the stakes a little bit and you combine, say, left cancelable and right invertible, that's strong enough to give you a morphism. So left cancelable and right invertible does imply isomorphism. Well, I think this lecture's gone on probably too long. I almost got through everything I wanted to talk about. I wanted to talk about initial and terminal objects, but that'll have to, I think that probably should wait for another lecture. To conclude, please leave a comment. I do want to hear your thoughts about whether you want me to continue or not doing these lectures. It's, a certain amount of work, and so please let me hear from you one way or the other. There's one other thing I wanted to mention, which just hang on one second. Okay, this is sort of a commercial. I have some reluctance to do this, but I'm going to anyway. In the early mid-'80s, I wrote a book on discrete mathematics, an introduction to discrete mathematics. For a couple of years, it was very popular, the leading seller, according to the publisher. It's elementary. It's at the lower end of the range of discrete math books for freshmen, sophomores. But some issues happened. The publisher changed hands, and the book got kicked around between different publishers. And in fact, nobody even told me this was happening. And so the book kind of fell out of use. Recently, I got the copyright back on this book, so it's now mine. And if you are looking for a discrete math book for a class you're teaching, an elementary discrete math book, I hope you'll at least take a look at this. You can go to my website, www.sroman.com, and get some more information about it, or you can send me an email through the website if you have any questions. So please excuse the commercial, but I'd hate myself if I didn't do it. So there it is. Thanks for watching. Bye.